Okay, right now we are recording. Okay, so that's the file which I call class 4 with the date 16th of September, where we entered the data mining step in the KDD process. Okay, so I go through this quickly just to repeat what we saw yesterday. In the data mining step, we mainly speak about clustering or classification or regression. First one is a unsupervised technique. Classification and regression are supervised techniques. There are others, association, summarization, and so on. The difference between supervised and unsupervised learning, maybe that's a bit more important. So I go here on the presentation mode. If we observe a database where we have observations in the rows, independent variables as columns x1 to xn, a dependent variable y, then we call supervised learning any model that tries to explain the dependent variable y as a function of the independent variables x1 to xn. Just 1 second. Okay, so you're still showing that you're here. Okay, so supervised learning is to build a model, which we call here a function f, which takes as input the independent variables x1 to xn and tries to explain to a dependent variable y. The variables we are seeing here are those variables that result from the previous step, which survived, let's say, feature selection, data pre-processing, transformation. So those are the final variables that enter our model and that went through the previous steps. Okay. Now, if the variable y takes numerical values, then we speak about regression. In which kind of application do we have numerical values? We would like to explain. For example, Jan? You know, in which kind of situation do we want to explain a numerical value as a function of independent variables?
You're talking to me, right?
Yeah, Jan, please.
Yeah. Sorry, just a second. I guess in any kind of, okay, so not sure, but maybe when it's about monetary values?
Exactly. For example, monetary value. For example, if you want to estimate income a person has. So in many applications, you don't know the income a person has, but you know their age, maybe their educational level, the place where they live, and you can estimate, well, I guess this person earns around 2,000, 2,500 euro, for example. But there are applications where you want to estimate the income as precisely as possible, for example, or other applications where you want to predict rainfall, for example, the level of rain of tomorrow. So what's the level of rain you're expecting tomorrow, which is also a numerical variable. Predicting, in general, a numerical value belongs to regression. For example, if you want to predict the price of a stock of tomorrow, so the Lufthansa stock or the Bayer stock of tomorrow, that price at the stock exchange would also be a regression model. Okay, on the other hand, if the variable y takes one out of few values, then we speak about classification. If y takes 1 to m possible values, where m is a small number, like for example 5, 7, 10 roundabout. So you want to, in that case, you want to classify your observations into one out of m classes. Okay, and if m takes, in a particular case, value 2, then you want to classify your observations into two classes. That's what we call binary classification. And that's maybe the application we use most. And that's the one I'm showing here with two classes with symbols plus and minus. So binary classification could be visualized like this. We have a feature space for obvious reasons. I'm showing just two features. Each symbol here is located in the position where we have the feature values of each observation. For example, this observation belongs to class minus and has a certain value for x1, certain value for x2. And building a model for binary classification means separating the two classes. Of course, in this case, we have some errors, type 1, type 2 error, or false positive, false negative. Okay, whereas unsupervised learning does not need any label, does not need the value of the independent variable. We just want to understand the pattern among the independent variables x1 to xn. So each observation has the same symbol because we do not have any dependent variable y, and we want to find similarity among observations. That's, for example, clustering, an application we saw yesterday. Okay, so instead of a linear model, we could also have a nonlinear model, which has the potential to generate less errors. For example, this case over here with a nonlinear model is on the right side, well, on the correct side, whereas this one here still is wrongly classified. So nonlinear models have the advantage to provide better results. That's an advantage. A disadvantage is they're more complex. That means it's more difficult to develop nonlinear models, and also it's more difficult to interpret nonlinear models. Okay. Then we switch to clustering. Go through this quickly. We need the notion of distance, very important. Again, distance is provided only by data that belong to a numerical scale, could be interval, proportional, or absolute scale. If we have data from the nominal or ordinal scale, then they don't provide distance. There are some, let's say, some special cases I will mention later. Similarity is kind of an inverse concept to similarity. Here we have an example of different distance measures. Euclidean distance is the one we use most. We saw also cosine similarity, which is of course not a distance measure, but it makes sense to have it on this table. By the way, the table is not mine. It's from the paper Xu and Wunsch published in 2005. So in a strict sense, it would be an error to put the similarity measure on a table that is called, oh no, they made it the right way. They said similarity and dissimilarity measure for quantitative features. Okay, it's always good to read the text. So we have quantitative features. That means you can see there is another expression. Quantitative means numerical, means interval or proportional or absolute scale. So here we have another expression, quantitative features, also called numerical features, but we know that it refers to or interval scale or proportional scale or absolute scale. So similarity and dissimilarity measures, where dissimilarity is understood as distance, couple of distances, and there is point symmetry, distance, cosine similarity. Okay. Here we have an example of a so-called distance function for categorical values. It does not meet the criteria we need for a real distance. Okay, so it's the Hamming distance calculates something like a distance for categorical features. Sounds like a contradiction. It's not a contradiction because it can be used for to calculate something like a distance if you have categorical feature values. Categorical means nominal scale or ordinal scale, but this distance function does not fulfill all three criteria we have for a real distance function. Okay, but anyway, it gives you a notion of distance if you have categorical features. we spoke about agglomerative clustering, visualized by this graph, where we merge classes based on the distance. As you can see here on the y-axis, we use Euclidean distance. Okay. If there are questions, please interrupt me. This one was agglomerative clustering. Agglomerative means we start on the finest level, the where each observation belongs initially to its own cluster, and we aggregate until we have just one cluster. At the other extreme, that's agglomerative clustering. Divisive clustering is the other way around. We start with all observations in one cluster, and then we divide. And that's the one we applied for a community detection in social networks, called the Gervin-Newman algorithm. Okay. In traditional clustering, you can also have the divisive case. Okay. And then we turned our attention to so-called partitional clustering, where we observe where we have all the observations and we partition the space of all observations. We introduced the k-means algorithm together with the notion of fuzzy logic. Okay, so first we had a brief introduction to fuzzy logic. That was clear. Any doubts regarding fuzzy logic? Basic idea is we don't classify, or we don't interpret observations as black or white. So we have in between levels of gray. For example, the notion of a young customer cannot always be decided as young or not young. There is a smooth transition between the two extreme concepts, young versus not young. Okay, there are applications where it makes sense. For example, customer segmentation. You know, if we want to describe behavior, maybe then it does not make sense to say someone belongs to the young group if their age is between 20 and 32, full stop. That would be maybe too harsh, because someone moving from 32 to 33 years in one day, the day of their birthday, does not change their behavior from one day to another. So that would be too strict. On the other hand, of course, there are applications where a strict threshold makes sense. For example, in the legal context, you're allowed to drive a car if you're 18 years old. One day less, you're not allowed to drive a car. It's still 18 in Germany? I don't know. I think so. I think in the US it's 16. Okay, anyway, I think you got the idea.
Driving with 17, but only if your parent is present at the same time.
Okay.
Maybe a question, an application of this fuzzy logic, because I was thinking about harsh barriers in a way, and the way taxation on income works would be a good idea maybe to also apply the transitioning to taxation, no? Because there's some point where, so I don't know if this is the English word, cold progression, kalte Progression, where at some point you earn 10 euros more and you have to give up a whole lot more to, in taxes. Do you know whether some countries are applying this? I guess no.
I don't know.
Okay.
Yeah, but anyway, it's a strict threshold. If you earn €1 more, then you pass the threshold.
Yeah, that's what I mean.
You can have several thresholds. That could be. So if I think that's the tax system in the US, here in Chile as well, which is stepwise constant. Okay, so if you pass one of the steps, then you have to pay more taxes. But anyway, it's a strict threshold, and that's how laws are, and laws have to be like that. The case of fuzzy logic typically is used if you want to describe some, let's say, fuzzy behavior. For example, your desire to buy a product. Yeah, some people they like to buy a skateboard if they are young, and young in that case would mean between, you tell me, 13 and 18. Jan, you're using skateboards still?
No, but for example, Frank Thelen, who is like 40 or something, or even 50, still skateboards. But yeah, I totally get the point. Like young till 20, maybe I would say.
Yeah,
I
but there is
consider,
no fixed point.
yeah, exactly. Makes total sense.
Yeah. Okay, so that was the idea of fuzzy logic, to model a, let's say, smooth transition between one extreme and the other extreme. Okay, we applied fuzzy logic to clustering. Maybe one important comment in order not to confuse: clustering is independent from fuzzy logic. It's not, it doesn't have to go together. Okay, you can do clustering without fuzzy logic. What I'm doing here is I introduce one technique called fuzzy c-means, which applies the notion of k-means, which is traditional clustering, together with the idea of fuzzy logic. But it doesn't have to go together. And that's what we can see here. For a given database, just consider the red dots, please. We apply traditional k-means and we get this result. You can see here on the right. So that would be possibly a result we obtain applying k-means clustering. And k-means is, I would say, still the most important technique for clustering. But on the other hand, if you add fuzzy logic to k-means, then you could get a result like this one here. Sorry, didn't fix it, but I think you got the idea. Each point now has 2 degrees of membership. Each observation belongs to class 1 and to class 2 at the same time. Okay, so for example, this observation over here belongs mainly to class 1, which we have on the left side with 86%, or I should say a membership degree of 0.86. It belongs to class 1, but it also at the same time belongs to class 2. On the right side, you can see the membership value each observation has, but just to class 2. So on the left side, I display the membership values of each observation to class 1. And on the right side, we have the membership values of each observation to class 2. Each element has 2 degrees of membership. One that tells us how strongly does it belong to class 1. And the second value for the same observation, how strongly does it belong to class 2. So that's an important difference to classical segmentation. In fuzzy segmentation, each object belongs to all the classes at the same time, but with different degrees of membership. Okay, how can we obtain the centers here, those blue crosses, in the traditional case, k-means clustering, but also in the fuzzy case with fuzzy clustering? In both cases, those blue X show the cluster centers. So what we need is cluster centers and degrees of membership. And we don't have to determine those elements. We don't have to determine cluster centers. We don't have to determine membership values. That's the job the algorithm does. What we do have to determine is, you remember, what does the algorithm need to start? Which kind of information?
Number of clusters.
Number of clusters, very good. So here we have a rough idea of the algorithm. We do need see the number of clusters beforehand. The algorithm does not start if we don't tell him the number of clusters. And that's an issue. We don't know the number of clusters beforehand. But for the moment, we assume the number of clusters to be given. Then we introduced the algorithm, and later we saw a way how to determine the number of clusters, having an algorithm that works only if it's got the number of clusters. Okay, and one element which was important here is a distance function. So in order to run the algorithm, we need the number of clusters. That's one thing we as users have to bear in mind. And we also need data that allow to calculate distance. We cannot do clustering with ordinal data. The problem is the algorithm does not understand this context. It's up to us to understand that we cannot apply clustering if we have features that belong to a nominal scale. For example, if we have a customer database where the features are age, income, perfect, they allow for distance calculation. But if we additionally have the city where people live, and we codify the city by numbers, we say Aachen is replaced by 1, Cologne is replaced by 2, and so on, then the algorithm could perfectly use these numbers to run and to calculate a distance. The algorithm does not understand that the numbers 1, 2, 3 codifying cities belong to the nominal scale. It's up to us to understand that. Okay, so take care when you're running clustering, you can use just numerical features. Okay, the algorithm iteratively calculates in steps 2 and 3 the centers based on membership values, that's formula 2, and then the membership values based on centers. So it's iterating between steps 2 and 3. Please don't look into detail with these formulas, just to mention one interpretation. That's formula number 2 here, where we calculate centers. In engineering, or engineers call it the center of mass. Okay, Massenzentrum. Okay, so that's the center of mass we observe. So if we have, for example, a cloud over here, then we calculate the center of mass of this cloud. And that's how the algorithm works. Iteratively, it pushes the centers to the center of the values for the centers to the center of mass. Okay, until a stopping criterion is fulfilled. The details are not important here. That's code which we have readily available. I mentioned yesterday R code for k-means clustering, but here are some more details. If you want to go into details, that's not the aim of this course. Some motivation. What do we need? Customer segmentation. If we want to understand segments of customers that are similar to each other. For example, if you want to promote some products, you don't want to offer all products to all customers without making any difference. That would be one extreme. Another extreme would be to offer the particular product to each customer. That would be the other extreme. Customer segmentation is kind of in between, where you group together similar customers and you offer products to the entire segment. Okay, all this is not new. We saw that yesterday. I go through this quickly. What we can see here is the methodology to determine the number of clusters. Now that we do have a method, in this case, fuzzy c-means, could be also traditional k-means without fuzzy logic. Okay, so each one of those two methods works if we provide the number of classes. And now we introduce the idea of a methodology in order to determine the number of classes. So I just run the algorithm with the candidate number of classes. If we have a clue, maybe the number of classes is between, let's say, 6 and 10, then we try clustering with 6, 7, 8, 9, and 10 classes. For each number, the algorithm provides me a solution, and then it's up to me to decide which one is best. And best, again, depends on some criteria, which we will see on the next but one slide. Okay, so we applied this methodology in a toy example. We came up with a solution with 6 classes, where each row represents the cluster center. And that's the way how we can interpret all customers that belong to that class. Okay, so customers that belong to class A supposedly behave similar to the center of class A. So they are around 32 years, they have an income around 2,000 euro, and so on. How do we determine number of clusters? As I said before, we just run the algorithm applying using different numbers of clusters, and then we need some criteria, for example, ACISS criterion or Bayesian criterion, to say, well, the one with 7 classes is best, or the one with 8 classes is best. Okay, so you got the idea. In order to run the algorithm, we have to establish the number of classes. We don't know that beforehand, so we run the algorithm with several numbers of classes, and then we select the solution that fulfills best one of those criteria. The fact that there are several criteria also tells us something. There is no correct solution. If there would be the one correct solution, we would not have different criteria. So the number of clusters is not a precise correct number. Okay, there are several elements to it based on, and we can determine the number of clusters based on different criteria. Okay, how to validate a solution? So once we do have a solution with a certain number of clusters, then we can do validation. We introduced the Davis-Boulder index, which basically relates compactness of classes with being separated among classes. So we want classes to be as compact as possible and as well separated as possible, one from each other. That's we measure with these two values, SI, that's the mean distance each object has, or all objects have, to their class center. And that's how we measure compactness. So we want SI to be small. SI being small means the objects that belong to one class are close to its center. Okay, it's a compact class. SI for class I should be small. And Dij, that's the distance between the two centers of classes I and j, we want that value to be as large as possible. That means classes are very well separated. So the Davis-Boulder index somehow mixes two elements into just one value. It's looking for a cluster solution where classes are compact and well separated at the same time. So again, don't look into the formula. The formula tells us we're looking for solutions where classes are compact and well separated. Okay, so a formula always has, or I should say always should have, a conceptual interpretation. And that's interpretation behind the Davis-Boulder index. It's not the only one. As you can see here in the first line, there are many indices to validate cluster solutions, but maybe that's the most common one. And that's where we finished yesterday. I just showed the R code. I showed also how to use it in R. And of course, you're free to use any other software tool to run k-means. It's not necessary to apply fuzzy c-means. If you want to, you can do so, no problem. But from now on, you do have a piece of code to run k-means, and that can be used in the context of our course for community detection. If you want to do community detection, doing clustering on the nodes without considering links, okay? And that's it where we finished yesterday. Any doubts so far? Questions, comments? Please think about it. We'll be back in a second with more coffee. Okay, here we go. Any questions so far? Nothing new so far today. That's what we saw yesterday. Okay. Again, everybody on the list of attendance, which is our chat for the moment. So everybody present. Very good. So we saw the difference between supervised and unsupervised learning, k-means, as well as fuzzy c-means, as well as agglomerative clustering, as well as divisive clustering belongs to unsupervised learning. We don't need and we don't use the dependent variable y. Okay, Miriam, thank you. Now we switch to classification, which belongs to supervised learning. Now we do have a, how shall I say, a dependent variable, again, a visualization very similar to the one we saw. That's from the publication, which is relevant for the exam tomorrow. A very basic paper, but important, still important. It's from 96, no, that's not correct. It's not 2006. I think it's 96. Yeah, again, this paper is not a very present current paper. It's from, I think it's from 1996. I don't know why. Maybe it was a updated version. Anyway, so but it's still important because it gives a very good and easy to read introduction. So here we have again the notion of classification. We have observations. Each symbol here represents, for example, a customer in a credit scoring database. Okay, and the customers belong to one of two classes, maybe good and bad buyers. We want to offer the loan to good buyers. Sorry, we want to offer the loan for good payers, and we don't want to offer a loan to those that have a bad repayment behavior. Okay, and what do we have as information for each customer? We have income and debt, maybe debt on previous credits. So what we're looking for is a model, in this case, a linear model to separate between good and bad customers. There we want to offer a loan and where we don't want to offer a loan. And again, we have error one X on the wrong side, one circle on the wrong side. We have two types of error, exactly what we saw before. Still a linear model. A nonlinear model would be able to have less errors, but it's more difficult to interpret. We saw that already before. And now we're going into one technique, one particular technique. It's a decision tree where we want to separate two classes. Who of you knows? No, maybe I better ask the other way around. Who of you does not know decision trees? Could you please raise your hand? So please raise your hand if you do not know decision trees. Okay. Okay, if you do not know decision trees, please raise your hand. Okay, thank you. Those of you who know decision trees, could you explain how it works? How does a decision tree work? Maybe using this example. Now, as observations, we have cars, 6 cars. For each car, I do have 2 independent variables, its weight, its HP, horsepower, and the dependent variable now is fuel consumption, which again, Jan, would be an example of a variable with numeric values. But in this case, we have categories of fuel consumption, high, medium, low. Okay. Afterwards, we will see the case of fuel consumption with a numeric value. That's called regression. But now we are doing classification. We want to classify cars into one of 3 classes, high, medium, low fuel consumption, based on weight, and HP. So who of you knows how decision trees work and can explain how it works? Okay, so you can see here, Moritz Jürgens, please. Moritz, decision trees.
Yeah. So I think I would start with, so a node, which is then the car, and then you can start to split it into cars with a low, a medium, and a high weight. And then from these new nodes, you can go through the horsepower, and then every car which has a low weight can then have a high horsepower, low horsepower, or medium. And then you can go one deeper to the fuel consumption. And so, you split up the whole tree.
Exactly. Very good. So that's the way the tree works. We start with all observations in one node. That's the root of the tree. And as opposed to nature, this tree grows upside down. Okay, so it starts with the root and it grows down. We split this node into several nodes using the information some of the attributes provide. So what's the aim of the split? Why do we split, Moritz?
Yeah, then you can see in which node. So for example, in the end, you have, let's think about it, you have 3 times 3 times 3, so 27 nodes in the end. So like on the bottom of the tree. And then you can see how many cars do you have in which of these 27 nodes.
Yeah, you're correct. In the case you would split using all the attributes, but that's not necessary. But we'll come back to that later. But it was correct, you said.
Yeah, sure. If you just have 6 cars, then you don't need to do this. Yeah, but it's also helpful to see on each level. So how many medium, high, low weight cars do you have, and so on. So
exactly, very good.
Gives you a better structure.
Yeah, very good. Did you apply decision trees and which kind of application, please?
So not to structure data set, more to see which kind of decisions I can make in a situation and what a decision would have as a result.
Okay. Yeah, great. Let's see how that works here in the toy example. Again, I know it's a toy example, but it helps me to introduce the basic notions we have here. So we split our node. Coming back to the questions. Why do we want to split? What's the aim of a decision tree? Look at the initial node. So we have 6 cars all together, and now I'm considering just the dependent variable, fuel consumption. That's the one I would like to predict. Okay, Jagmor, just 1 second, please. So look at the distribution of fuel consumption in this node. Everything is mixed. You have 2 cars with high consumption, 3 with low consumption, and 1 with medium consumption. Everything is mixed. And that's what you don't want to have in a node. You prefer to have nodes that have only cars with high or low or medium fuel consumption. So you want to come up with homogeneous nodes. But it's not the case here. Everything is mixed. You have kind of chaos in this node. And Jagmor, how can we proceed? That was your comment in that context?
I was going to answer the question, but
yeah, please go ahead with your comment.
So on why do we split? Question. Okay, so we split because first of all we are trying to find relevant attributes, let's say, because not all of them can be relevant for the information. And
correct.
After finding them, for example, let's say that HP is the most relevant one. because, for example, when the HP is high, the fuel consumption is always high, let's say, then we can always say that if we split from that node in the beginning or later on, we can actually classify two things. Like if it's high, it will be high kind of thing. So this is why we split.
Yeah, very good. Very good. That's correct. We'll come back to some of the elements you mentioned during the development of the tree. So let's start first assuming one attribute, assuming weight as the first attribute. So we split the first node using weight. Those cars that have high weight finish or end up here. Those with medium weight end up here, and those with low weight end up here. Okay, so question now is, what does it tell us, this level of the tree? Moritz already said, so each level tells you something. And here we have already some kind of information. For example, what we know in this case is all cars with low weight, they do have low fuel consumption. Low weight is car number 3, low fuel consumption, and car number 5, low fuel consumption. So what does that mean in plain English? We don't need any other information. If we know a car has low weight, that's already sufficient to conclude it's going to have low fuel consumption. At least that's information hidden in this database. And in this context, in my opinion, a decision tree is a technique that works in the way of the KDD, represents best the notion of KDD. KDD, knowledge discovery in databases. So we do have a database with 6 cars. There is knowledge inside this database, but even in this toy example, it's not very easy to see what's the relation between the two independent variables on the one side and the dependent variable on the other. And the decision tree kind of reveals that information. It discovers knowledge in the database. And there is one piece of knowledge we just discovered. We found that cars with low weight have low fuel consumption. That's not obvious even from this simple toy example. It's not easy to see that cars with low weight have low fuel consumption. Knowledge discovered in databases. Okay. Another piece of knowledge is found here. We don't need more information. If a car has medium weight, it has medium fuel consumption, at least in our database. I'm not saying it's always like that. So in our database, and that's the only source of information we have, we don't have anything else. We don't know anything about cars and so on. The only information we have is our database. So in this database, the knowledge inside our database tells me that cars with medium weight have medium fuel consumption. I don't need any other information. I can stop splitting here. As Moritz said, this level already tells me a lot. Tells me a lot about half of my entire database. 3 out of 6 are already classified. Okay, that's not the case for cars with high fuel consumption. We have C2, 4, and 6. C2 has high fuel consumption. C4, well, C or car 4 has also high fuel consumption, but car 6 has low fuel consumption. So it's not sufficient to know the weight, that the weight is high in order to, well, kind of predict. It's not predicting because we do have the database already, but it's not sufficient to know a car has high weight in order to establish fuel consumption. With other words, we need more information. We need more information, for example, based on HP. So we continue splitting, and now it's obvious what happens. Each car ends up in its own node, and now we can finish the process, because in every node we have only examples from one class. I know it's ridiculously small, the example, since in each node we have only one observation. Of course, we can stop here. so there is no contradiction inside the nodes because there's only one car. But that's due to the number of this toy example, the number of observations in this toy example. Multiply the number by 1,000, so you would have 1,000 cars in this node here, and all have high fuel consumption. That means I don't need any other information apart of weight and HP in order to establish fuel consumption. Okay, questions so far? Any doubts or additional comments? Okay, so with this technique, a decision tree, we revealed information in a database. We discovered knowledge in databases, KDD. And the final step is we can generate rules, okay, if then rules from this tree, reading each path from the root to a leaf, from the initial node to a terminal node, like this. If weight is high and HP is high, then fuel consumption is high. Whereas another rule would be if weight is low, then fuel consumption is low. That's knowledge we generated from our database, and this knowledge can now be applied to new observations. That means to a car we don't have in our database. If a new car appears, we put it into the root node, then it goes through the tree, and the prediction for its fuel consumption would be according to the fuel consumption attached to each terminal node. So if a new car has high weight and low HP, then it's considered to have low fuel consumption based on the knowledge we learned from our database. Okay? Any questions so far?
But then, like, what is written on the left side is wrong, right? Then it should be in the last sentence, then the fuel consumption is low and not high.
If weight is high and HP is low, then fuel consumption is low. Yeah, you're right. That's an error. I did that on purpose for you to see, for me to see if you're with me.
Okay, perfect.
No, just joking. Okay, yeah, very good. Yeah, and sometimes it's good to have some mistakes on the slides. No, it was, of course, it was not on purpose. Thank you very much. Yeah, but of course you're right. So if there are no further questions, I do have some questions. What about the level of the scale of our independent variables, weight and HP? Weight we usually measure in kilogram or something like that. But now we have medium, high, low. Why is that? In a decision tree. Because we split, and if we had, let's say, a numerical value, I don't know what the weight of a typical car is, maybe between 800 kilo and 2 tons, I don't know. If we had weight as kilogram, and each car would have a value between 800 and 2000, then we would have how many? 1,200 splits here, one for each value. That, of course, does not make sense. Okay, that would be a too fine granulation. So one message here is, in order to build a tree, we need categorical variables for the independent, sorry, we need categorical data for the independent variables. Okay, so in order to have splits that make sense, we cannot use data from a numerical scale. Maybe interval, proportional, or absolute scale cannot be used in order to split. We have to do some categorization first. We need categorical variables for the, sorry, we need categorical data for the independent variables. First message. And another message, excuse me, Jagmar, just a second. Another message, when we spoke about missing values, I don't remember exactly who it was. Someone said, well, if we have missing values, we can work with a missing value as such. The decision tree is a technique that could use the information the value is missing. So if we, for example, if we would not have the value of HP for car number 1 and for car number 4, then we could split here. HP is high or medium or low or missing. You understand? So if we would have missing values, in that case, in the case of a decision tree, it would not be necessary to impute a value. We could use the information this value is missing as an additional branch. Okay. So Yakmo, you had a comment, question?
I actually had a question about, you said that we need to have independent data as categorical, but for example, can't we use it just as numerical? For example, if it's something below 2, it's this way and the other way is that way, kind of thing. Because I've seen that was done before, I think. That's why I want to test.
Yeah, of course. If you have numerical information, weight as kilogram, for example, from 800 to 1000, from 1000 to 1500, then you can split into categories. But in order to run the tree, in order to construct the tree, you need categories. So there is a way of kind of pre-processing you have to do on numerical values before you run the tree. And of course, there are software tools where you can enter numerical values, and internally, the software tool determines categories. So you as a user, you don't have to decide how to determine these categories. There are software tools that do it internally, which has advantages and disadvantages at the same time. If they do it internally, it's pleasant for the user, you don't have to think about it, but on the other hand, you can't think about it. So you leave the decision to a software tool. So maybe you would like to come up with these categories. Anyway, in order to construct the tree, you need categories. If you do have numerical value, you have to do some categorization. You have to define intervals. I think that was your comment.
Exactly, thank you.
Okay, yeah, thank you. So one question was regarding scale. We need categorical variables. Another question is, why did we start with weight? Why didn't we start with horsepower? Kelvin, please.
Because it gives us the most information gain.
Exactly. So again, we started here where we have all cars, all observations in one node, which means a mixture of different classes regarding fuel consumption. I don't like that. It's too much mixed up, different cars of fuel consumption. What I prefer is something like this, where in each node we do have only observations from one class. And again, since the toy example has very small numbers, there is just one observation in those nodes. Just think of larger numbers. So multiply the number of observations by 100, for example. So anyway, so what we want is to have nodes where all observations belong to just one class, like here. Here we don't have any mixture of different fuel consumption classes. We have what we call a homogeneous node. This node is homogeneous because all its observations have the same fuel consumption. That's what we want to obtain. What we have here in the root node is exactly the contrary. We have everything mixed up. That's a chaos. And as Kelvin said, that's what we don't like. We want to have gain in information. And there are several measures, mathematical measures, that determine this gain. One is entropy. entropy is used in, well, basically in two areas, thermodynamics, in order to measure how two elements are mixed. For example, two gases, how strongly we have the mixture. That's used in thermodynamics, but also we use the notion of entropy in information theory, developed by Shannon. Yeah, there is a nice movie I saw recently. I don't remember the title of the movie. Maybe I can share it. For those of you who like history of science, I found it quite interesting. So Shannon in the 40s developed information theory using the concept of entropy. There is one comment on the chat. Jan, Tenet? What do you mean with Tenet?
Is that the movie's title by Christopher Nolan, like where they go back in time because of entropy? That's the movie you saw, or am I completely off?
No, I don't think so.
Okay.
I saw it recently. I don't remember Tenet. Actually, it's not a movie. It's a documentary with interviews where they have interviews with Claude Shannon.
Okay, never mind then.
Yeah, okay. I will share the link. I found it nice. It's like history of science, but you have to be, I don't know, mathematician to like it, maybe. I liked it. Okay. So what we are using now is the notion of entropy in order to select the best criterion, the best attribute to start splitting. We used weight, but why did we start with weight? Why didn't we start with HP? The answer, we know the answer now due to the development Shannon started, is given here. Again, please don't look into the formulas. Just one word is important here, entropy. Okay, we need the notion of entropy of a node. The entropy measures the degree to which different classes are mixed inside a node. So for example, note the root node, the first one, this one here, has 6 cars, 1 with medium, 2 with high fuel consumption, and 3 with low fuel consumption. Terrible, everything is mixed here. So applying entropy here would tell us there is a huge mixture of those pieces of information. That's the idea Shannon had in information theory. Okay, the question now is, which of the available attributes helps me to reduce entropy? And entropy measures the degree of mixture of those pieces of information. Okay, let's see. There is one definition with the logarithm, but never mind. I'm not interested in formulas. Of course, there are software tools that apply these formulas. I prefer to show the notion of entropy on this slide. In the case of just 2 classes, let's assume we have fuel consumption high or low. Let me look to the chat. The bit player, exactly, Alexander. Yeah, that was the name. The bit player. I liked it, and I can share the link. Nice movie. Thank you, Alexander. So entropy is shown here as, yeah, this curve here, the upper one, but it's not the only one. What do we measure here? So on the x-axis, we have the probability that a car, in our case, belongs to 1 out of 2 classes. So we have cars, and let's assume instead of having 3 classes, in the simplest case, we have just 2 classes, high and low. So the probability that a car belongs to class high ranges from 0 to 1. If it is 0, that means, no, let me start with the opposite case. If the probabilities of all cars in one node to belong to to one class is 1. That means all cars belong to the same class, high fuel consumption. That's one extreme. In that case, do we have any chaos? Do we have any mixture of information? No. In that case, what we call here the impurity index is 0. And the impurity index could be any of these values, entropy or Gini or misclassification error. So there are many concepts to measure the degree of mixture of information. In this case, we just use entropy, but the message here is it's not the only one. So if all cars belong to one class, then we are on one extreme and no mixture. Entropy is 0. If, on the other hand, in the other extreme case, no car belongs to this class, means they all belong to the other class, we also don't have any mixture of information. Entropy is 0. In which case do we have the worst value of entropy if the probability is 0.5. And as you can see here, all of these measures reach their maximum value in the case of 0.5. So if we have a mixture of, let's say, 50-50, 50 cars belonging to high fuel consumption and 50 cars belonging to low fuel consumption, that's the perfect chaos, which we don't want to have. The entropy tells us that we have the worst value in the case of 0.5. So again, entropy based on this formula tells us how strong does weight contribute to reducing the mixture. So we apply entropy to this level. We calculate entropy of this node. How much would it be? What's entropy of this node here? No, there's no mixture. All observations belong to just one class. Do we have any chaos? Do we have any mixture of fuel consumption here?
No.
No, that means here entropy is 0. Okay, that's one extreme case. Here also entropy is 0. All observations belong to the same class. Sorry for the confusion, because here entropy is introduced for just 2 classes, and here as well, only 2 classes. In this example, we have 3 classes, but the argument holds anyway. So if all observations belong to just one class, that means entropy is 0. That's the case here. That's the case here. We have 2 classes with entropy equal to 0. And here, entropy is not equal to 0, because we have high, and low fuel consumption here. So we are somewhere, maybe somewhere here. 1/3, no, here, 1/3. That's the entropy we have. It's a positive entropy. Yeah, in this node, we still have some mixture of fuel consumption high and low. Okay, so the information provided by this node is not 0. That's the interpretation Shannon gave to the entropy. He said, this node here, fuel consumption low, where we have car 3 and car 5, this node does not provide any information. Yeah, it's on the level 0. Entropy is 0. Since we don't have a mixture, information content of this node is 0. Everything belongs to the same class. Okay, whereas information transmitted by this node here is not 0. There is a mixture of observations. There is more than just 0 information. So that's the interpretation of entropy in the context of information theory. Okay. So again, when we decide which attribute to use, we could use Gini coefficient or entropy or any other impurity index. Details are shown here. Details are still not important. That's a visualization of entropy. And now we know how to select the attributes for the next split. Okay. Another comment, another question. Try to imagine we are not in a toy example. Try to imagine we are in a real case where we have, let's say, 1 million customers with 50 attributes. And we want to do binary classification. We want to classify customers into good or bad customers. Binary classification. Okay. So we have all customers in the first node, in the root of our tree. And we want to split, again, using a decision tree where hopefully at the end, we have in each terminal node only customers that belong to one class, or good customers or bad customers. Okay, so that's what we are aiming at. We use entropy to determine the first attribute, the most powerful attribute to reduce entropy. Okay, so let's assume we have 50 candidate variables and we select on the first level variable number 17. Okay, so we use variable number 17 for the first split because according to entropy, variable number 17 is the most powerful. Then we observe the result and we still cannot finish the tree construction. We have to continue. Then we choose attribute number 23. Then we use attribute number 37 and so on. And maybe we come up with a tree where we can classify all customers correctly without using all available attributes. You're with me? So we have 50, let's assume 50 attributes as candidate variables. We build the tree by using only a subset of those 50 attributes. How is that called? What we just did? From all attributes, we used a subset. How do we call that? Jagmur?
Feature selection, maybe?
Very good, very good. That's feature selection. So now we understand that a decision tree does two jobs at the same time. It's a technique for classification and implicitly it selects features. If it does not need all the available attributes, if the tree works with a subset of available attributes, we do simultaneously classification and feature selection. And let me switch, please, to another presentation we saw earlier this week. Just a second. I think it's this one here.
We still see the old one.
I know. I just found it. You remember this one here? Feature selection. That's what you can see now.
Yes.
Yeah. Okay. Thank you. So that was the presentation we had, I think, on Tuesday afternoon, where we introduced feature selection. And at that moment, I said, well, there are three categories of techniques for feature selection. There are some techniques that work as a filter, correlation, chi-square, and so on. There are some techniques that work as a wrapper, forward selection, backward elimination. I mentioned embedded methods, but we didn't go into detail. Embedded methods are techniques that do simultaneously classification and feature selection. The decision tree is one example. Yeah, the decision tree is considered a embedded method because it does feature selection and classification simultaneously. The feature selection module is embedded into the classification technique. Okay, so that's what I wanted to mention now. A decision tree does implicitly feature selection, and that's why it's considered a embedded method. It's a technique that does both jobs at the same time, simultaneously. Both jobs, I mean feature selection and classification, by just using only those attributes that are necessary. Okay. Going back now to the tree, you can see the decision tree now again. Yes or no?
Yes.
Okay, thank you. So a decision tree is a embedded technique. In this case, we see on the screen, it does need all available attributes because we have just 2. But in a real setting where we have 50, 100, or even more available candidate variables, maybe it does not need all of those. And that means it does classification and feature selection simultaneously. Okay, so that's what I wanted to mention in the context of a decision tree. That's the criterion. On the very last line, it tells us how should we split. We select the feature with minimal value for information measure. IM is defined as the information measure based on entropy. So that's what Shannon defined back in the 40s, 50s. Information measure based on entropy. So that tells us what's the most important feature. Select in each branch, as we can see here at the bottom of this slide, select in each branch the feature that minimizes information measure, which is based on entropy. And there is still an error on this slide. Where's the error?
The M and the I and the M have to be switched.
Very good, very good. So IM has been introduced here as information measure. At the bottom, it's MI. That's still Spanish. You know, in Spanish, compared to English in general, the order of the words is exactly the other way around. I don't know, Miriam, if you agree with me. MI means medida de información. So it's measure of information. In English and in German, we would say information measure. Informationsmaß. Okay, so instead of MI here at the bottom, it should be IM to stay consistent. That's it. Okay, that's the way a decision tree works. It splits attributes using a impurity index. Could be, for example, entropy. It could be, for example, Gini. There are many indices. And it does feature selection simultaneously to classification. Those are the takeaways I want you to, well, take away from this presentation. Formulas are not important at this moment. A decision tree is a technique for classification where we need categorical attributes. Okay, values should not be numerical. We need categories. We need a impurity index to split, for example, entropy, and it does simultaneously feature selection. That's, let's say, a high-level takeaway from this technique. Okay. Any other questions so far? Yeah, okay. Those of you that are in data mining, knowledge discovery, data science, big data, maybe you heard or used already random forests. That's a more advanced technique. That's a more powerful technique than a simple tree. Okay, as the name suggests, a forest. What is a forest? A forest is simply a set of trees, as in, let's say, natural language. A forest is a set of trees. The same happens here. There is a technique for classification called random forest that simply uses several trees. So I have one tree on this side, tree number 1, tree number 2. In total, we have n trees. Each one is used to classify a observation. So, for example, tree 1 classifies our observation as class A, whereas tree number 2 classifies the observation as class B. They don't agree. These two trees don't agree. But that's exactly the power of a random forest. We use a set of trees, maybe 10 different trees, here just shown as n, 10 different trees. Each one gives its classification, and then we need something to aggregate their classification. For example, majority voting. So I take the result from each one of the 10 trees, and I go with the majority as my final classification. Okay, and as we know from literature, but also from practical experience, random forest is a very powerful technique. Yeah, it's comparable to more advanced nonlinear techniques. It goes beyond a simple decision tree because it kind of uses the power of different trees. It allows for different, let's say, classifications. It allows for some errors, but then by majority voting, the idea behind majority voting is the majority most likely will be right. And that's very similar. If you want to classify a customer and you ask just one person, maybe this person gets it wrong. But if you want to classify a customer and you ask 10 experts, then, and you just listen to what the majority tells you, then most likely the 10 experts together will give you a better prediction than the single person. Okay, that's very similar. In a random forest, you consider each one of the trees as an expert, and a set of experts, a group of experts in general decides better than one single expert. Let's say interpretation of a random forest, joining several trees. Anyone with experience using random forests? No. Yakmur, did you use random forests?
Yes, I have actually.
Yeah. Could you please tell us in which area, please?
For example, one of the things I used it was to, okay, I did it mostly in the projects because I'm still studying my master's, but for example, one of the questions were like, it was about an insurance company and whether there's a fraud in insurance or not. It was a classification problem like that. And yeah, I used random forest for that and it worked very well actually.
Okay. Yeah, thank you. Thank you very much. Alexander Gladys?
I used them in my master's thesis where I compared different classification algorithms in an application to classify smartphone usage based on sensor data.
Great.
So
great.
for example, if you hold it in a landscape mode, then you're most likely watching a video, stuff like
What
this.
were the techniques you used in your benchmark?
I think I compared KNN, random forests. I think logistic regression was there as well, and SVM maybe. Yeah, it's been a few years.
Yeah, standard techniques. By the way, all the techniques you mentioned, except KNN, K nearest neighbors, but all the other techniques you mentioned are on the presentation, which you can see now on the screen and which you have available. I uploaded the presentation as it is. I didn't cut it, but we don't have the time to see all of the techniques in this presentation. Yeah, okay, so far I have shown decision trees and random forests. We will also go into logistic regression. The presentation, which you see on the screen, also contains SVM, support vector machines. It contains also neural networks, I don't know if we will go into each one of these techniques. I don't think so. Okay, but yeah, that's it. Thank you. Looking at the time, it's now 12:30. We have 30 minutes left. Anybody needs a break? We can have a short break now. What's the general opinion? We continue? You want to break? 5 minutes?
Probably continue and then make the big break.
Okay, so we will finish at noon German time. It's noon. No, it's 1. Okay, sorry, got it wrong. Now it's 12:30. It's right. 12:30
Yeah,
in Germany. Yeah, thank you,
that's right.
thank you. So we will finish at 1 p.m. Okay. Yeah. Okay. Interesting. Different to Chile. In Chile, in a class here via Zoom, they wouldn't allow 90 minutes in a row. We are now already 90 minutes in a row teaching. Impossible here. Interesting. Okay, so far we spoke about the decision tree for classification, where we want to classify observations, in our case cars, into one of here 3 classes. Here we have an example of classification which is not binary classification, but classification with 3 classes: high, medium, low. Okay, so we introduced a tree which uses entropy, could be any other criterion for impurity. And then we saw random forest as a combination of several specified trees. You can consider a tree as an expert specified on a certain task. So this tree has been trained in order to, let's say, classify correctly certain types of cars. So maybe it gets it correctly in some cases, but not that much correct in other types of cases. That's why we prefer to listen to what the group says. We want to listen to the majority. If some of the trees gets it wrong, could be, we guess, majority will always outperform each single tree. Yeah, that was important. Yeah, so if we apply a random forest, let's say 100 times, maybe once this tree number 1 gets it wrong, and in the other case, the tree number 1 gets it correctly. But in general, we can say that in that majority voting outperforms each one of the experts. And that's very similar to what we observe in, let's say, real life. If we speak to a group of experts, the majority voting in general would give better results than each one of the experts. Okay, I think I said the same thing already 2 or 3 times. Well, next step, here we apply random forest, not for classification, but for regression. What does regression mean? We have observations. Each dot here is an observation. We have a couple of independent variables. Here I'm showing just one independent variable, x1, and we want to predict a numerical value, y. And the example could be, for example, predicting income, which is a numerical variable, or predicting stock prices, and so on. So we want to come up with a function f that takes all independent variables in order to predict a dependent variable, but in regression, the dependent variable now is a numeric value, real number. Okay. So the so-called regression tree starts with a database with the structure we have here. We have observations, same thing, 6 cars. We have independent variables, which still have to be categorical, but now difference is my dependent variable is numeric. Okay, the dependent variable y is numeric. And well, I go through this a bit faster because it's very similar. There's only, let's say, only one difference. Branching is still the same. Yeah, for branching, we use the candidate variables, which are on a categorical level, which are categorical variables. So we still can split using high, medium, low for weight. We still cannot use weight as a numerical variable. But now the fuel consumption inside each node is given by numerical values. For example, C3 and C5, what's their fuel consumption? 5.2 and 5.0. Do we need more information? Do we have to continue branching here in this node with C3 and C5? They are very based on your gut feeling. Do we need more information for prediction? Here we have 5.2 for C3 and 5.0 for C5.
Perhaps we need to calculate how similar these two categories are close to each other.
Exactly, very good, Yi. We have to calculate variance or any other measure. So what was entropy or Gini in the classification case, that's now variance. In the regression case, it's variance, the criterion that tells us if we are supposed to continue branching or if we could stop. So variance here is very low. 5.0 and 5.2 liters for those two cars have a very low variance. Just looking to the chat. So would you mind also explaining the assumptions, premises behind those models? That's what Yi said on the chat. Assumptions are we have attributes with categorical variables and a dependent variable with numeric values. There is not more we need to know. Those are the assumptions. Yeah, that's fine. So during the algorithm, we split, okay, but the entropy now is replaced by something like variance, because when we have numeric values, we cannot calculate entropy. To calculate entropy, we have to have classes. So what was entropy in the classification case is now variance or some similar criterion in the regression case. Variance here is low, so we stay here, we don't continue, and we say the prediction for a new car that ends up in this node will be the average, 5.1. So one observation has 5.0, the other one 5.2, average is 5.1. So if the day after tomorrow a new car arrives where we know weight and HP, but we don't know fuel consumption, and if weight is low, then our prediction of fuel consumption for this car would be 5.1. Okay. Same here, of course, since we have just one case, variance is 0. And prediction would be 7, because that's exactly the fuel consumption car number 1 has. Again, toy example, few cases we have here, but I think you got the idea. Whereas those 3 cars have high variance, C2, 10.6, C4, 9.8, car number 6, 4.8. So we observe here a high variance. Question is it acceptable or not? And that's exactly the part of the algorithm I would like to skip. So the question here is, are fuel consumptions we observe here too heterogeneous? That's a question, and we need to define some criterion to say we stay with this variance we observe here, as was the case here. Here variance is very low. Question here is if it's acceptable or not. And I don't want to go into detail. Those are details of the algorithm. Message here is only there is something called a regression tree which does regression using the notion of decision trees. Okay. If you want more details, here are the details. The stopping criterion is if the variance, as you can see here, is below a threshold. And there is the detailed algorithm there in the third but last line. You can see the word threshold. That's the criterion we have to establish in order to decide if we continue branching or not. Again, that's not the aim of this course to go into details. I want you to know that there is a technique called decision tree. It can be used for classification as well as for regression. We saw the classification case with a bit more detail, and we also introduced the notion of a random forest. Okay, so that's it I wanted to say regarding decision trees. One technique we can use for classification or regression. In both cases, of course, it's supervised learning. Okay, so maybe the last 15 minutes we can use it for another technique I have here on this presentation, which are association rules. Important in the context of social network analysis, important in the context of recommender systems. Think of the case beer and diapers, or of the case of Amazon, Netflix, for example, where we receive recommendations based on other people's behavior. So the basic technique for all these recommendation systems or recommender systems is the technique of association rules, which I'm going to introduce now. For example, we observe a database of supermarket transactions. Think of each ticket. So you leave a supermarket, you pay the goods you bought, and the ticket you get, those are the transactions we are analyzing. So we have a ticket where we have several products, SKUs, stock keeping units, but anyway, we consider it as products. And the question now is, which products go together? For example, we mentioned the case beer and diapers, but there are also many other applications in this context. The algorithm to run association rules is called a priori. Don't want to go into details. I just want to show the basic notion of this algorithm, which uses two concepts. One is confidence. Anyone has experience with association rules? Any experience? Or maybe I should ask the other way around. Who does not know association rules? Could you please raise your hand? Please raise your hand if you do not know association rules. Okay, yeah, thank you. Anybody here who knows, who has experience with association rules? Maybe you can share your experience. Yes or no? Those that did not raise your hand, Paul Schmidt, for example. Paul, any experience with association rules? Okay, no experience. Yeah, so I'm going to introduce the basic notions we are using here. One is confidence. So if we had one rule that says X implies Y, for example, beer implies diapers, that rule could be a result of our algorithm, but then the next question is it a good rule or not? X implies Y, is it a good rule or not? What does it mean a rule is good, gives some information? There are different measures to tell us something about the quality of a rule. One measure is confidence. So the question is, how confident can we be with this rule? X implies Y. In which case you would be confident with such a rule? let's say in plain English, what does confidence mean? If I tell you X implies Y, what does it mean? You feel confident with this rule.
It means it's quite certain the result that we are sure.
Okay, go on. That's fine. It's certain. Who mentioned that, please? What's your name?
Semahat, yeah.
Semahat? Okay, it's certain. So I'm confident with this rule. I believe in this rule if it's certain, if it applies often. That's not the only criterion we're going to introduce, but let's start with this one. And let's see it on a very simple toy example. We have now a small supermarket, very small supermarket with just 5 products. Products 1, 2, 3, 4, 5. Those are the products we have in our supermarket. And the supermarket has only very few customers. So what we can see here are the transactions, let's say the tickets of the only 4 customers we had so far. Customer 1 bought products 1, 3, and 4. Customer 2 bought products 2, 3, and 4. Customer 3 and customer 4. Okay, and now I'm telling you, Semahat, one rule is 2 and 3 implies 5. What's your confidence? Well, the answer is on the screen, but maybe you can explain why it is 100%.
It implied all the observations we have in the dataset.
It applies in each one of the cases. No, let's say it the other way around. It's correct each one of the cases it applies to.
Okay.
So this rule, does it apply to the transaction, to the first transaction? The rule, does it apply to the first transaction? No, because the rule applies only if the left-hand side is fulfilled. In the first transaction, we don't have the left-hand side. We do not have products 2 and 3. So the rule does not even apply to the first transaction. So I can't say it's correct or wrong. It does not even apply. Okay. In transaction number 2, it applies because we have 2 and 3. Here in transaction number 2, the rule applies and we have 5, so it's correct. It applies means the left-hand side is given. In transaction number 3, it also applies and it's correct. We have 5. In the fourth transaction, it does not apply. So confidence of our rule is 100%. Each time it applies, it gives a correct answer. Yeah, if we had, for example, let me put it right here. If we had another transaction 2, 3, and 4, so if that would be, it's not the case, if that would be another transaction in our database, the rule would apply, but it would give a wrong result. If that would be my set of transaction, what would be the confidence of the rule 2, 3 implies 5?
Around 70%, maybe.
Very approximate, 2/3.
Yeah, 2/3.
The rule applies, or no, the rule applies in 3 cases: in transaction 2, in transaction 3, and in transaction 5. It applies in 3 cases, and it is correct in 2 out of 3, 2/3, 66, well, 0.6%. Okay, got the idea? Any doubts so far regarding confidence? Well, the general definition is given here. A rule has confidence C if C% of all transactions in T which contain X. Yeah, that's important. We reduce our analysis to those transactions that contain the left-hand side. And if they also contain y, then the rule is fulfilled. So in the rule 2 and 3 implies 5 has confidence 100%. So let's do the following exercise. I'm just copying this page. Now I can kind of eliminate all this. Okay. Just a second. And now I ask you to tell me other transactions which also have 100% other rules. Please tell me rules where confidence is 100%. For this set of transactions, which rule has also confidence 100%?
Can I say that 5 leads? Can I say something like, if they buy 5, they wouldn't buy 4, 100%?
Just a second, let me come back. Rafyandi said 1 implies 3. Rafyandi, how do you do the math?
Because every time 1 is there, there's also 3.
Exactly. Okay, other rules. Who had the comment before? Sorry for interrupting you.
I'm sorry. Can I say that 5 will be sure for sure? This, if he buy 5, he will not buy 4. Can I say something like that? Then no 4.
That's not part of the basic definition. Of course, it makes sense to say product of the purchase of one product implies not purchasing another product. But the not notion is not part of this definition. But I understand your idea, Yi.
Thanks. Thank you.
Yeah, thank you. So any other rule here?
I would
Another
one.
5 implies 3. What's confidence?
5 implies purchase of 2 would have 100% confidence.
What did you say? 5 implies
purchase
2?
of 2, and that would have 100% confidence. Also, Professor, the first one, wherein 1 implies purchase of 3, in the second tabular, there's no 1 there, but still 3 is there. So the percentage would reduce, right? It won't be 100%.
Which one? Which rule?
The first example, that is 1 implies 3.
Yeah.
If you see in the data set, the second value, that is 2, 3, and 5. There is no 1. So the percentage would reduce, confidence percentage.
You're saying this is not correct?
Yeah.
Yeah, but so please, Rafyandi, you have to define. You have to defend your suggestion.
But this implies every time 1 is there, so it only appears 2 times in the first and the second, so it's 2 times 1, and then 3 every time there's like, yeah. But if 3 it's not 1, can you say that, like, it doesn't have to be the same, right? Because 3 to 1, then it will be like 1, 2, 3, 4.
Yeah.
1, 2, 3. It's going to be 2 per 3
3 implies 1 has which confidence?
It's going to be two-thirds.
2/3, okay.
Yeah,
Well,
I got it.
let's put it this way, 66.6%, 2/3, okay? So what we can see here is it's not symmetric. Confidence is not symmetric. If we change the order of left-hand side and right-hand side, then it gives different confidence, okay? Okay, again, I'm not teaching basic arithmetics. You got the point? I'm not teaching that. I'm teaching understanding of the notion of confidence. What does it mean? We have a certain confidence in a rule. Yeah, we are saying someone who buys beer also buys diapers. That's a rule. Beer implies diapers. And we have to understand what does it mean? This rule has a certain confidence. Mathematics at the end is trivial, but the question is, what are we looking at? Okay. There was another comment on the chat. Yeah, Alexander says X implies X, has always 100%, very good. 1/4, Christoph said 1/4 implies 3. How much? What's the confidence, Christoph?
It's 100%.
Yeah, it applies. Okay, that's a nice example because it's 100% confidence, but look at this. It applies only in 1 out of 4 transactions. And this example, 1/4 implies 3, tells us also something, a shortcoming of confidence. What's a shortcoming? I could say a rule with confidence 100%, it's a perfect rule. 1 and 4 implies 3. Perfect rule, it has confidence 100%. No, it's not like that. Confidence has a shortcoming. What is it?
We see it only one time. There's only one instance of that. So
maybe it applies in few cases. So this rule applies only in one transaction. So it doesn't apply very often. And that's the motivation. I'm sorry, we are beyond the time, but just to finish this part, that's the motivation for the next definition, support. Support now takes into account the volume of your business, of your transactions. Same example as before, the rule 2 and 3 implies 5, which had confidence 100%, now has a support of only 50%. What's the definition of support? A rule X implies Y has support S if S% of all transactions contain X and Y. But the important part now is this one here, of all transactions. Now we relate our rule to the entire volume of all transactions. So how do we measure it? 2, 3, and 5 together. 2, 3, and 5 together. Do they appear here? No. Do they appear here? Yes. Do they appear here? Yes. Do they appear here? No. 2, 3, and 5 together appear in 2 out of 4 transactions. That means support 50%. And going back to the example Christoph mentioned before, 1 and 4 implies 3. What's the support of this rule? 25%. 1, 3, and 4 is present only in 1 out of 4 transactions. Okay, so it's easy to have a rule with a high confidence. It can be very specialized. If you have 1 and 2 and 3 and 4 implies 5, yeah, then confidence would be 100%, but support 0. It doesn't apply, never. It never applies. But it's always when it applies, it's correct, yes, but it doesn't apply. You get the idea? confidence is looking at one issue of a rule, and support is looking at another issue. So if a rule is good or bad depends on several measures. One is support, another one is confidence, and in total, there are, in literature, we found more than 20 criteria to tell us if a rule performs well. Support and confidence are the most important ones. And we will finish now, yeah. No, it's not overfitting. Yeah, I understand your point, Jagmor. It's not in literature, it's not considered as overfitting, but yeah, you could understand it as overfitting. If it's a very, very specialized rule, then it has a very high confidence. It makes sense to call it overfitting. I never saw it as overfitting in literature, but I understand your point. It very rarely applies, but in those rare cases when it applies, it's always correct. That's, let's say, the interplay of support and confidence. Again, recommender systems use something we call association rules, and association rules work using these concepts, support and confidence. And that's all I want to say by now. And we're going to have our lunch break now. Okay, you're welcome, Jagmor. There is a third definition, don't want to go into detail, just mention it, lift of a rule. There is another definition, we can measure lift, and there is the algorithm. So that's what I wanted to mention in the context of association rules, which are the basis for recommender systems. Okay, the famous beer diaper example, but also what Amazon does when you buy a book, the website offers another product saying customers who bought this book also bought another book. For example, recommender systems on Netflix, Spotify are based on the notion of association rules. Of course, those are much more sophisticated techniques nowadays, but it started with the notion of association rules. And now we have a first understanding of what confidence and support means. Any questions so far? Okay, so we are well beyond noon, no, well beyond 1 p.m. So we start again, let's say 2:05 p.m. Okay, 1 hour from now. Okay, enjoy your lunch.
Thank you, you too.
Thank you.
Okay, see you. See you 1 hour from now. Bye-bye.